So there was another question on whether the fact that we allow the boundary of the body to be broken up into two subsets, one of which we have traction on and the other on which we specify displacement conditions, whether this introduces some sort of discontinuity in the problem. So picture that prompted the question has got to be this one. So we have the body in the current configuration, we have a traction boundary, right? Right, and this is where we're saying T equals sigma n, right? That is the traction condition. And here we have the rest of this is the displacement boundary. And here we're saying U equals U bar, right, on this part of the boundary. And the question is that, all right, so we specify U as a field, we come all the way, but what happens here? Don't we have a discontinuity there and there? Because if we were to march along the displacement boundary, we would see that yes, we're controlling the displacement everywhere, and let's suppose we have a continuous function there, that U bar is a continuous function along the displacement boundary. But now what happens when you reach the traction boundary, because you stop controlling the displacement there? Okay, this situation, by the way, is very common, and in fact it happens in almost all solid bodies and most fluid bodies as well. So in the context of this of our prop, right? So we have the basis. It's as if, okay, I'm holding it at this end, right, with my right hand, and I'm going to let's suppose that I'm holding it. Let's suppose that my hand is very rigid and it doesn't move. It doesn't even get pushed away by the body or anything. And on this end, I'm now applying a force, right, with my left finger, with the index finger of my left hand. So you can look at that as a traction condition, right? And now, what about the rest of the body? Well, the rest of the body also I have traction conditions. It just happens that traction is zero. Okay, whatever you see as a free surface does indeed have a traction condition that is zero. But now the question is, okay, what about the place where I'm holding it with my hand here, right? Where, if at this point, just where my finger ends, what's happening, right? Suddenly I'm no longer controlling the displacement there. So yes, even though in terms of the way the boundary condition is specified, there may be a discontinuity in that I'm controlling the function U bar right until here, and then at this next point, there is no more U bar. U bar isn't even defined there, in fact. Okay? However, the governing equations of mechanics, which are the following, right? So the governing equation of mechanics is one of the governing equations is the balance of linear momentum, right? Which is rho. I'm going to start using this symbol now, just so that it's shorter to write. Okay. Now this involves a derivative on the stresses, right? And it involves a divergence of the stress. What we're going to see later on, in just a few more segments, is that we will actually relate the stress to some function of the displacement, right? So we're going to see that the stress depends upon the displacement in some way. Okay. I don't want to say too much about that, because that will really start us up on the next topic before we really get there. But by so doing, what we're going to see that this partial differential equation is a partial differential equation that controls the derivatives of the displacement, and therefore controls the smoothness of the displacement field. Okay, and by so doing, the PDE make sure that we have sufficiently smooth solutions U, even though in terms of the boundary conditions, it may appear that we have a discontinuous way in which we are specifying the boundary conditions. Okay, so what this amounts to is that the partial differential equation controls the smoothness of the displacement field U. Okay, as a function of space of position and time. All right, and so even in the case of this apparent discontinuity in the specification of the boundary conditions, the solutions themselves are continuous, right? As a further example, just remember that even when we have a point load is not just discontinuous. A point load is even worse. It's a delta function, right? So this doesn't look like a delta function, but assume it were indeed a sharp arrow. Okay, so you have a delta function there. Even in this apparently extreme case of actually a singular boundary load, the partial differential equation ensures that the solutions are continuous. Okay, and that just comes from the study of the partial differential equations and how, by having more derivatives in it, we are controlling the smoothness. Okay, so we could get into more details about this, but that would really require us to say much more about the PDE even before we actually get down to talking about it systematically.